In this video, we're going to look at the one-dimensional diffusion equation, also known as the one-dimensional heat equation. So we're going to consider a rod of uniform cross-sectional area A oriented along the x-axis. And we're going to consider the heat budget between position x equals alpha and x equals beta. The temperature along the rod is going to be given by phi as a function of x, which is position, and time t. A is the cross-sectional area. Now the volume of the rod between x equals alpha and x equals beta is given by, and so the mass of the same segment of rod is given by the integral of the density. The rate of change of the thermal energy content of the rod is, by definition, going to be given by the following. And so the thermal energy content rate of change is given by the integral from alpha to beta of phi sub t times the specific heat, C, times the density, times the volume. So C is the specific heat. The constant C is determined in the lab by measuring the rate at which the temperature increases as a function of the amount of energy put into the rod. And we're going to call this rate R1. Now there's another way in which we can get the rate of change of the thermal energy content, and that's by measuring the heat conduction through the cross-sectional area at x equals alpha and at x equals beta. Now we're going to assume that the sides are insulated except for the two ends. So that's going to be the heat flux through x equals alpha minus the heat flux through x equals beta. And the heat conduction is proportional to the temperature gradient along the rod, and it goes from regions of high temperatures to low temperatures. So that means this will be equal to minus K, where K is the heat conductivity, times the derivative of phi with respect to x, evaluated at alpha, and times t, times the cross-sectional area, minus, so K is the thermal conductivity of the material. And we're going to call this quantity R2. Now clearly R1 has to be equal to R2 if the sides of the rod are insulated and there's no internal generation of heat. This is a conservation principle, that the time rate of change of thermal energy is equal to the flux in through the sides. There's no spontaneous generation of thermal energy. And so we can then equate these fluxes to this integral, which means we have the integral from alpha to beta so the minus and the minus makes it a plus, so we have d phi dx at beta and t times k and a minus d phi dx at alpha t multiplied by ka. Now the right hand side here is the same form as the integral of an exact differential, so this can be rewritten as the integral from alpha to beta of d by dx of k phi of x and t times the cross-sectional area. And so this can be written as an exact differential of the k d phi dx x and t. So when we do the integral, we remove the derivative. And if we bring everything to the same side, we have the following: the integral from alpha to beta d phi dt c rho minus k d phi dxx, so the second derivative of phi with respect to x at x and t, times the area times dx is equal to 0. So we've taken this term and this term. Now just so you remember here, the subscript t just means the partial derivative of temperature with respect to time, and the subscript x is the partial derivative of temperature with respect to position, and phi xx is the second partial derivative of phi respect to x squared. Now this integrand here has to vanish uniformly if this integral is to be 0. And that's because alpha and beta, while fixed in terms of with respect to time, are arbitrary. So we could have picked our little segment to do our budget to be anything. And if the integrand didn't vanish, then we can always pick alpha and beta where the integrand will always have the same sign. In which case we'll be summing a bunch of quantities of the same sign, and there's no way we can get an average to 0. And so that means the integrand has to vanish uniformly. So this implies that d phi dt times c rho minus k phi xx is equal to 0, which we rewrite in the following way. Phi sub t is equal to kappa phi sub xx, where kappa is defined as k divided by c rho. So this is the heat equation. If we look at the dimensions of the various quantities we've introduced, maybe we can start by kappa. So the dimensions of kappa are equal to the dimensions of phi sub t divided by phi sub xx, which are equal to the dimensions of inverse time divided by inverse length squared, or a length squared per time. And that means that we can now try to define the dimensions of the conductivity, because we should be able to find the dimensions of c and rho. So let's start from the beginning. Dimensions of x is position, length, t is time, phi as dimensions of temperature, which I'm going to denote by a theta, a area, rho is the mass density, mass per length cubed, c will be the energy per mass per temperature increment. And so the dimensions of k, the conductivity, are going to be equal to the dimensions of kappa times the dimensions of c times rho. And kappa as dimensions of length squared over time, c as dimensions of energy, mass times temperature, rho as dimensions of mass per unit volume. I'll be left with a 1 over length, a time, an energy on the top, and a temperature on the bottom. So the conductivity is going to have units, for examples of joules per meter per second per degrees. Alright, so this completes this video on the derivation of the heat equation. The next thing we're going to do is show how to solve it numerically using finite differences.